All right, guys, welcome back. So, congrats on finishing chapter 3 and having another chapter down in the books. So, that means today we are going to start chapter 4, and we are going to begin by looking at waves and the electromagnetic spectrum. Okay, so you're probably thinking, what does this possibly have to do with chemistry? So, we're going to revisit our old pal Rutherford. So, we learned about him in the first half of chapter 3. And he developed our most recent model of the atom that we have looked at. Okay, so the last model of the atom we looked at was Rutherford's, where we had our nucleus at the center of our atom, and that contained our protons and our neutrons. And then in the area around that nucleus, we said we mostly had empty space and our electrons floating around. But we didn't talk about what our electrons were doing in that space. And that is what chapter 4 is going to look to answer. Is in our atom, what the heck are our electrons doing? So inside our atom, what are electrons doing? That is our big question for the unit. Okay. So before we can understand what our electrons are doing, we need to take a look at waves. Because matter can emit and absorb light. Okay, and this is where we're going to come into terms of the model of our atom. And we know light is going to act as a wave and a particle. So it has kind of two different behaviors going on at the same time. Okay, and this understanding is going to help us look at what our electrons are doing in our atom and develop our understanding of the atomic model. Okay, so waves are really cool because they transmit energy through the movement of particles. Okay, so they transmit energy through the movement of particles. We are going to have two different properties when we're looking at waves. We're going to have our wavelength, which is going to be the distance between our crests. Okay, so the crest, that is going to be the peak of our waves. Okay, so then the wavelength would be the distance in between these two peaks. Okay, we are going to represent that with the unit of meters, and we are going to use the Greek symbol lambda to represent wavelength. So whenever you see lambda, that's talking about wavelength and the distance from peak to peak. We can see in this first example, we have a short wavelength because those crests are very close to one another. But in our second example, we can see that we have a long wavelength because those peaks are very far apart from one another. Okay? The other property of our waves that we're going to look at is our frequency, and that's the number of crests that pass per second. So we know our waves are moving as they transmit energy. So if we were to pick a point in time and we counted how many crests pass this point per second, that would tell us our frequency. Okay. And we are going to use the Greek letter, nu, to represent frequency. Let me redraw that again, make it a little clearer. Kind of like a little fancy V. Okay, so the number of crests that pass per second is going to be frequency. We notice our top wave, since it has a short wavelength, the number of crests that pass by are going to be greater because we're going to have our crests closer to one another. Okay, so since our crests or our peaks are closer to one another, we're going to have more passing through a single point. Whereas our bottom wave, we can see that our peaks are farther apart, so it's going to take longer for them to pass through that point. So we're going to have a lower frequency or a lower number of peaks per second. Based off of this observation, we are going to come up with a relationship between wavelength and frequency. And we are going to see as our wavelength gets bigger, increases, that means our frequency is going to decrease. Okay, so as our wavelength gets longer, we're not going to have as many peaks passing through per second because it takes longer for those peaks to get to that point. On the flip side, as wavelength decreases, our frequency is going to increase because as those peaks get closer together, it takes less time for them to pass through a given point, and we're going to have more passing through per second. Okay. We are actually going to see a multitude of different waves in our everyday life. They are surrounding us every minute of every day. So the electromagnetic spectrum shows us waves of different frequencies and wavelengths, okay? And depending what frequency and wavelength we have determines the type of wave that we are looking at. So if you think about microwaves, that's obviously going to be the microwave that's used to heat up your food, but it's also going to be the radiation that's coming from your cell phone or from your Wi-Fi router. The visible spectrum, this guy, those are the waves that you can see with your eyes. Okay, those are the colors that are visible to you. Those are the only electromagnetic waves or type of radiation that you are actually able to see. Okay? UV waves, these are obviously from the sun and what help you tan in the summer. Whereas X-rays, that's the radiation that's shot through your body whenever you get an X-ray, if you have a broken bone or something like that. Okay, so we are honestly being surrounded by all these waves every day. And we can see that each wave has a breakdown of different frequencies and different wavelengths. If we look at these microwaves, these are going to have the longest wavelength. Okay, because 10 to the negative first is a lot bigger than 10 to the negative 12. So that means our gamma, these guys have the shortest wavelength. Okay. And again, looking at our relationship between wavelength and frequency, we look at these. Gamma may have the shortest wavelength, but it has the highest frequency. So as we move down that spectrum, we can see that our frequencies get smaller and smaller as our waves get longer and longer. Okay. So microwave, these guys have the longest wavelength, but the shortest frequency. And that also tells us we're going to be moving the slowest. Okay. So based on the wavelength or frequency of a type of wave, we can determine what type of radiation we have. Okay. And this is going to become in a super handy when we are looking at our model of the atom. Okay. So you're probably wondering, how on earth could I possibly calculate my wavelength or my frequency? Lucky for you, we're going to have an equation. So the equation that relates wavelength and frequency is going to be V is equal to wavelength and frequency. Okay? So our wavelength and frequency of a wave are related using this equation. Where C is the speed of light. That's because waves travel at the speed of light in a vacuum. Okay? And that can be constant. And then, of course, our length represents wavelength in meters, and our nu represents our frequency in hertz. Okay. So if we know our wavelength or our frequency, we can calculate the other using this equation. The speed of light is always going to have a value of 3 times 10 meters per second. Okay. So if we look at this first example, we want to find the wavelength of a wave with a frequency of 1.079 times 10. So we can find the wavelength by using this equation. We'll set C, or 3 times 10 to the 8th, equal to our wavelength times our frequency, 1.079 times 10 to the 12th hertz. We're already in hertz, the right unit, so we don't need to do anything extra here. If we want to get wavelength by itself, we're going to have to undo that multiplication and divide each side by 1.079 times 10 to the 12th. This again is where that E button on your calculator is going to become super handy because then we don't have to worry about parentheses. But when we do this, we should find that our wavelength here is 2.78 times 10 to the negative 4th meters as our wavelength. Okay. So if we wanted to, we could go back to that electromagnetic spectrum and see which one has a wavelength of 2.78 times 10 to the negative 4th. And we are going to see that's our infrared waves. Okay, so for infrared, we see that 10 to the negative 4th. Okay. In the second example, here we're solving for the frequency of a wave with a wavelength of 500 nanometers. So again, we're going to use the equation that 3 times 10 to the 8th is equal to wavelength times frequency. Here we are given our wavelength, but it's in nanometers. If we look at our equation, we're always going to want meters. So our first step is going to be to convert our nanometers to meters. Thankfully, we're given this conversion that for every 1 meter, we have 1 times 10 to the 9th nanometers. So we divide 500 by 10 to the 9th. Again, that E button will become in super handy. And we'll find that our wavelength is 5 times 10 to the negative 7 meters. Now that we're in meters, we're able to plug this in to our equation. So we'll have 3 times 10 to the 8th is equal to 5 times 10 to the negative 7 as our wavelength times our frequency. Okay, so again, to get the frequency by itself, we need to divide each side by 5 times 10 to the negative 7. And we should find that our frequency here is 6 times 10 to the negative 14, and that's going to be measured in hertz since we're looking at frequency. So make sure before you plug values into your equation that your wavelength is always in meters and that your frequency is always in hertz. If we wanted to, we, just like our previous example, could go back to our electromagnetic spectrum and see what type of wave this is. Here, our wavelength was 500 nanometers, or 5 times 10 to the negative 7 meters. And we are going to see that this lines up with our visible spectrum. 500 nanometers exactly is going to line up with green light. Okay, so we have this wavelength and a frequency. We know that we are emitting green light. Okay. I hope this helps. The main ideas are that matter can absorb and emit light, and that light is going to act as a wave with a wavelength and a frequency. The wavelength and frequency are inversely related. So as your waves get longer, your frequency is going to get smaller and smaller, and vice versa. And we can categorize our types of waves using the electromagnetic spectrum. Okay, that looks at our types of waves based on their frequency and our wavelength. We can relate the frequency and wavelength of a wave using this equation, where C is always 3 times 10 to the 8th, lambda is our wavelength, and nu is our frequency. Okay, so that will always be our go-to equation if wavelength is in meters and frequency is in hertz. Please let me know if you guys have any questions. Otherwise, I hope you have a lovely day.